Okay, kinematic in 2 dimensions. We're going to use this model for cases where we're not moving in 1 dimension anymore. Now we're going to start moving in 2 dimensions. So we might be following a path. We're going to use the same technique. We're going to decide of a coordinate system, x and y in 2 dimensions. And the same way as we could use our displacement and position vector, we're going to do the same thing. So we're going to point to our position along the motion or the dynamics by using vectors, vector position, except this time we're going to call it r. So at point 1 we would use r1, at point 2 later in time we could use r2, at some later time t3 we are going to use r3, and so on and so forth. The basic formula that we used before are going to remain the same. A is equal to dv dt, and v we had dx dt because we're using a one-dimensional case. For 2 dimension, we're going to replace it by dr dt. Since r is a vector, we're going to be able to decompose it into 2 dimensions, the x dimension and the y dimension. So the same way as we could decompose a vector, any vector a, into one component ax along the x direction, another component ay along the y direction, we're going to be able to do the same thing with r, such that R1 can be decomposed as R1x and R1y. If now we're dealing with vectors, we're going to be able to decompose any vector v into two different vectors, the x component of the velocity along the x direction and the y component of the velocity along the y direction. So everything that we've learned in 1 dimension, we're going to be able to port it into 2 dimensions. And the way to do it is we're always going to decompose our motion into the x component and into the y component separately. The main application that we're going to be using is the application of a projectile, and we call it projectile motion, which is nothing less than the free fall case that we've used earlier, except instead of throwing the ball up or down, or just up or just down in 1 dimension, now we're going to throw it with a particular angle, so we can have a parabola shape, which will be defined in 2 dimensions. So now that we know where we're going, let's draw a typical parabola. Let's say this would be describing the dynamic of a particular point. Let's say at t is equal to 0, we're going to give that particle a particular velocity, initial, v0. Then at some later time, the velocity, remember, the velocity at every instantaneous velocity is going to be the tangent. So this would be v1. At some later time, this would be v2. Then v3 at the top. Then v4, etc., etc. So whenever we're going to be dealing with trying to explain and model this velocity, at each position, we're going to be able to decompose that velocity vector into two components, the x component and the y component, the x component and the y component, the x and the y, the x, so at the top it would be only x, then again the y, the x, the y, and the x. And we're going to treat each dimension separately. Now remember that for free fall, our point is always subjected to one particular acceleration, which is always pointing down. So at every instant, our particle is going to be subjected to the same acceleration, a, that we've defined as minus 9.81, whoops, whoa, meters per second squared, which is the one that we define as minus j. That's what we call projectile motion. We give the particle an initial force, which will create a particular initial velocity, and then this particle will follow a parabola, and at all instant in time, the only acceleration that this particle is subjected to is the usual, which is pointing down with a magnitude of 9.18. And at every instant, we're going to be able to decompose the velocity into two components, the x and the y, same as the position, which we will be able to treat separately.